MCV4U1 Chapter 4 Session 9. In this session we are working on Section 4.4 of the textbook, Concavity and Points of Inflection. Concavity and the second derivative. The graph of y equals f of x is concave up and an interval x greater or equal than a, smaller or equal than b, in which the slope of the tangent line to the graph of f of x are increasing. And this interval f double prime of x exists and it is greater than 0. The graph of the function is above the tangent line at every point on the interval. By looking at these two graphs, we'll see the slope of the tangent line is increasing, therefore function is concave up. As you see, the tangent line is below the curve. Similarly, the graph of y equals f of x is concave down in an interval in which the slopes of f of x are decreasing. And this interval f double prime of x exists and it is less than 0. The graph of the function, when it is concave down, as you see at any point on the interval, is below the tangent line. If f prime of c equals 0 and f double prime of c is greater than 0, c and f of c is a local minimum and the graph of y equals f of x. And if f prime of c is 0 and f double prime of c is negative, c and f of c is a local maximum. This is called second derivative test. If f double prime of c equals 0, the nature of critical point cannot be determined without further work. By knowing f double prime of c is 0, we cannot determine the nature of the critical point. Point of inflection occurs at c and f of c on the graph of y equals f of x if f double prime of x changes the sign at x equals c, from negative to positive, from concave down to concave up, or the other way around. All points of inflections on the graph of y equals f of x must occur either where second derivative is equal to 0 or does not exist, undefined. Let's sketch the graph of y equals x3 minus 3x2 minus 9x plus 10 from what we learned in this section. We find the first and second derivative. The first derivative is 3 times x minus 3 times x plus 1, and second derivative is 6x minus 6. First derivative is 0 when x is 3 or negative 1. F double prime when x is 3 is 12, which is positive, and when x is negative 1, it's negative 12 and it is negative. Therefore, x equals 3 corresponds to a local minimum and minus 1 local maximum. Concavity changes at 1. By drawing the sign chart we see before 1, the function is concave down since second derivative is negative, and when x is more than 1, it's concave up because second derivative is positive. We used second derivative test and we found negative 1 and 15 is local maximum, 3 and negative 17 is local minimum, 1 and negative 1 is the point of inflection. It is a cubic function with positive leading coefficient, therefore the graph starts from third quadrant and extends to the first quadrant. by joining these points, we have the graph of the function. Next question, next example. Sketch the graph of y equals x4. First derivative is 4x3, second derivative is 12x2. Second derivative is 0 at x equals 0, but otherwise is always greater than 0. This means 0 and 0 is not point of inflection of the graph of the function. If we draw the sign chart for first derivative, we'll see before 0, first derivative is negative, and after 0, it is positive. Therefore, 0 and 0 is local minimum, and function is concave up always. Let's sketch the graph of y equals x to the power of 1 over 3. The derivative is 1 over 3 cube root of x2. At 0 it is undefined, and when x is not 0 it is always positive. That means function is always increasing, and at 0 derivative is undefined. Limit of f prime of x as x approaches 0 is positive infinity from either side. Therefore, we have a vertical tangent line at x equals 0. Second derivative is negative 2 over x to the power over 9 times x to the power of 5 over 3. Before 0 positive, after 0 negative. Therefore 0 and 0 is point of inflection. Before 0 function is increasing concave up, after 0 increasing concave down. At 0, 0 we have a vertical tangent line. So this is the graph of the function. Last example, determine any point of inflection for f of x equals 1 over x2 plus 3. We find the second derivative of the function, 6x2 minus 6 over x2 plus 3 to the power of 3 is the second derivative. We set it to 0 by setting the second derivative equal to 0 axis plus minus 1. At 1, the value of function is 1 over 4. At negative 1 is negative 1 over. At both of them is 1 over 4. The function is even. Before negative 1, second derivative is positive. Function concave up. Between negative 1 and 1, second derivative is negative, function concave down. And when x is greater than 1, function is concave up since the second derivative is positive. 1 and 1 over 4, negative 1 and 1 over 4 are point of inflection because the concavity changes at these 2 points. In summary, the graph of a function f of x is concave up on an interval if f prime of x is increasing on that interval, and if it is decreasing on that interval, the function is concave down. A point of inflection is a point on the graph of the function where the function changes from concave up to concave down or vice versa. If c and f of c is the point of inflection of a function, then f double prime of c is either 0 or undefined. Test for concavity. We draw the sign chart for second derivative. Whenever second derivative is positive on any interval, that second derivative is positive, function is concave up, and if on an interval it is negative, function is concave down. Second derivative test. Suppose that f of x is a function for which f prime of c is 0. And second derivative of f of x exists on interval containing c. If f double prime of c is positive, f of c is local minimum value of the function. If it is negative, f of c is local maximum. If f double prime of c is 0, this test fails and we have to use first derivative test. To understand what we've done in this section, next session we are going to work on questions from page 205 and 206 of the textbook. Question 1 part A, question 2 part B, question 9 and question 10. Thanks for watching.